Welcome to another Aspire demonstration movie. In this one we'll demonstrate code and data mobility. This protection has been designed and developed jointly by Ghent University and the University of East London. In this case we focus on the security requirement of confidentiality of code and data and also integrity of the code and data in a program. In this case, data refers to statically allocated data that's normally present in the binary. Concrete requirement and goal is that we want to remove part of the code and data from the static binary. And instead it should be downloaded at runtime just prior to when the data will be accessed or the code will be executed, and this way we prevent static attacks on the code. This protection will also serve as the foundation for renewability protections, where instead of downloading the exact extracted code and data from the binary, new versions with different features can be downloaded on the fly as an application is running. So here we see the overall design taken from our reference architecture. On the left top you see the original application server. On the right you see the original application. You also see we have a code mobility server, and on a server we use a database that has access to a bunch of code blocks. These are called the mobile code blocks. In the original application some code was removed and instead stubs have been injected. When one of these stubs is reached during the execution, it invokes a binder, and then the binder invokes a downloader which connects to the code mobility server, after which the code server can send over a code block. This code block is placed at a random location on the heap in the application on the client. Other code blocks can be downloaded as well, and in our latest implementation these blocks can also be flushed and then they have to be reloaded at new locations. The fact that the locations of these blocks are randomized implies that code is not present at constant addresses, and this complicates also dynamic attacks such as the use of debuggers on the mobile code blocks. Now in the project, University of East London was responsible for implementing the server part and the communication logic. Ghent University was responsible for most of the client-side development, and we developed the binder and the downloader. In Ghent we also developed the tool support to extract the code blocks from a binary and to replace them with stubs that invoke a binder and a downloader, and the way this was implemented is through link time rewriting. As for other binary code rewriting protections, we rely on the Diablo link time framework developed in Ghent. Now the code blocks that we've shown here, they do not only have to contain code. How does that work? Well, in Diablo, if we look at its internal representation, we see that it looks somewhat like this. In blue here you see a regular control flow graph, so these are basic blocks, but this is not just a control flow graph. In Diablo we call it an augmented whole program control flow graph. We link the code of all functions, and moreover the blocks you see here in green and in purple, those represent data sections of the original object files that were linked into your program. And we also add edges from the code to data, but also from data to code. An edge like this from data to code means that a pointer to some code is stored in the statically allocated data. An edge from a code block to a data block means that somewhere here in the code an address is computed that points to this block. For example, for this block, the fact that only one edge points to this block means that the data in this block can only be accessed once this piece of code, which we call an address producer, has been executed at least once in the program. So in fact, this edge models that this data only becomes accessible if this piece of code is executed. Now to support code and data mobility, what we do is the following. Suppose we have annotated some code, it's this piece of code, and furthermore suppose this code contains the only reference to this data block. That means that we can safely extract the code and the data from the program. We replace the code by a stub. This stub will invoke the binder, and the binder and then the downloader will ensure that both this piece of code and the data will be loaded into the memory of the application running on the client device. That means that as soon as the first address producer of this block is executed, and so as soon as the address block might start to be accessed in the program, either in this fragment or very late, that doesn't matter, as soon as a reference might become available in the program, this data will be present because it will be loaded from the server. Now let's look at this protection in action. We'll show it on the SafeNet use case. That's the license manager. So let us first compile this application. going to speed up the log of the compilation because it's a little bit boring to just watch it. Okay, here it's done. Now, if we scroll back a bit, here you see that a script is executed, and this script in fact automatically uploads the code mobility blocks to the server and installs them in the database. You see that it inserts them for a certain application ID. This ID was automatically assigned to this application such that the server knows which blocks to send if any application that was compiled with the toolchain connects to this server. So let's have a look at the code that we actually protected in this run of the compiler. So the code that we'll protect here is the int hmac function. We annotate the whole function body with the code mobility annotation. And we mark that the code should become mobile, and also that the data accessed in this code fragment, and for which address producers are only found in this code fragment, should also be made mobile with it. Now in this case, this is the int hmac root. This is an array of byte values. So we expect that data to become mobile with the code. Now let's first look at the result in the build directory that we just created. We'll look at the binary code after stage 5 and the mobile blocks directory. We see there is one mobile code block. We also have some metadata. That's to inform the server about the data. That was the data that was transferred to the server earlier on. Now we copy the dynamically linked library, the protected version, from the BC05 directory to our embedded board. Before we execute it, we're going to start looking at the log of the mobility server. This was already running, and you see it already contains some logs for a previous application. But when we execute the application on the board here, you see that it requests a block from the client. In this case, our downloader prints this debug information, and you see that indeed the block was requested on the server. It occurs in the log, and also the size of the block and so on occurs there. Furthermore, we can show here by grabbing on the string of bytes. You see the bytes here in the program, and you can see that we grab for the exact same bytes, 5151 FC. So you see it recurring in the grab that we do, and we grab in the BC04 directory. That's the directory where the application is stored, the library, when it has not yet been rewritten by the binary rewriter that implements the code mobility. And you see that indeed this array of bytes was found in the library. In the BC05 directory, there the code has been rewritten, and you see that the sequence of bytes was not found in the protected library anymore. However, in the mobile block, you see there it was stored. So this kind of proves that the data was indeed moved onto the server, and it was no longer present in the ELF file of the protected library. The Aspire project has received funding from the European Union 7th Framework Programme under grant agreement number 609734.